Hello friends, in this problem there is a non-conducting ring of mass m, radius r, which is charged as shown. The charge density, that is the charge per unit length, is lambda. It is now placed on a rough non-conducting horizontal surface. At time t equal to 0, a uniform field is applied in the x direction and the ring starts rolling without sliding. We have to determine the force of friction acting on the ring when it starts to move. So let us first draw the diagram of this ring. So for this circular ring, this is the diameter which is horizontal to the plane. Now I am considering an element at an angle of theta having width of d theta, that is, let us take this particular element into consideration, that is the element formed between these two lines which has trapped an angle of d theta which is present at an angle of theta. So we know that the charge on this portion, as you can see, the charge on these two portions will be equal to lambda into r d theta. Charge on this portion will be equal to minus lambda into r d theta, as these two portions were having equal and opposite charges. As you can see over here, the charge density was lambda and the length of this differential element will be r d theta, that is the arc length. R d theta multiplied by the charge density will give us the value of dq. Now there is a electric field acting in positive x direction. So we can say that the force acting on this first element will be equal to lambda r d theta times of E, that is q into E. Similarly, on this negative charge, we know that the force will act in opposite direction. It will experience a force opposite to the direction of field. Now the net torque on these two elements can be written as force, that is lambda r d theta into E. This is the force multiplied by this perpendicular distance, which will be equal to r sine theta, and this expression when multiplied by 2 gives us the torque acting on these two differential elements. Since these two torques, the force due to these two torques will be added with each other. Now the net torque can be found with the help of integration of this torque. So integrating this expression with the limit from the proper limits from theta equal to 0 to theta equal to pi by 2 gives us the value of net torque, that is 2 lambda r square into E. Now after finding this net torque, let us assume that the friction is acting in forward direction. Since the charges on these two quarter rings formed were opposite to each other, that is lambda and minus lambda, the net force due to electric field acting in positive x direction will be 0. So we can write the only force in x direction is friction, which will be equal to mass into acceleration. Let us call this as equation number 1. Further, the torque due to friction can be written as Fr into R, and the clockwise torque provided by the help of this electric field is 2 lambda r square E. So the net torque will be clockwise torque, that is tau 1, minus this anti-clockwise torque provided by friction, that is Fr into R, which will be equal to I into alpha. Let us call this as equation 2. We also know that for pure rolling, we can write the value of A will be equal to R alpha. So condition for pure rolling is the value of A will be equal to R alpha. Now we can solve these three expressions by substituting the value of moment of inertia of the ring, that is mr square, and simplifying these three equations. We get the value of Fr to be equal to lambda r E naught. Further, this positive sign coming in the final result indicates that the direction assumed is correct, that is the friction will act in forward direction. So the net value of friction along with proper direction will be lambda r e naught in I cap or positive x direction. Thank you.